Let's get started with Unit 10. The first section introduces a lot of the ideas and vocabulary that we're going to need. So it says in 10.1, the I can statement is, I can understand and use the vocabulary and basic principles of vectors. So let's write the word vectors right here. Vectors. And it might seem on the simple side, but let's label the 4 cardinal directions on the compass dial right here. We got to make sure that we know these. So we go north, east, south, and west. You've probably heard never eat soggy waffles. If you've got that, that's awesome. And then what is a scalar? So remember, we use scalars with matrices. A scalar is just a plain old number. Plain old number. And I'm going to use a hashtag for that, make it a little bit quicker. And it says, what does the magnitude of an earthquake represent? Well, when an earthquake happens, they measure it with a Richter scale, and then they'll report what the magnitude is. And that basically represents how big that is. Now, another way to talk about this is magnitude is just a fancy word for the size of an earthquake. Okay? And we're going to use magnitude a whole bunch, so keep track of that. And then it says write down the Pythagorean theorem and the distance formula. So I'm going to write down the Pythagorean theorem this way. This is the way I like to remember it. I'm going to write down leg squared plus leg squared equals hypotenuse squared. And again, I abbreviate hypotenuse, HYP, hypotenuse squared. And then the distance formula is this. It's d equals, and then it's a big square root, and then it's x2 minus x1 quantity squared, and then y2 minus y1, y1 quantity squared. All right, so we've got the two of those. Those are definitely related. Hopefully you remember where those come from. And then you can write down the Pythagorean theorem as a squared plus b squared equals c squared. That's the way most people memorize it. The reason I like this is it reminds you what type of triangle it is, because if it's got a hypotenuse, it's got to be a right triangle. Hypotenuse is over here, that's the long side, and then the 2 legs are over there. Now, when we use scalars before, we use those with matrices, like we said a second ago. We're going to see scalars in a slightly different setting now. So a scalar is a quantity that measures only magnitude. So write the word magnitude, and we might abbreviate that a little bit later, but let's write magnitude for the time being. And remember, magnitude is a fancy word for size. So some examples would be something like this: 70 miles per hour or 50 pounds. They just measure how fast something is going, how much something weighs, or what the force is, or something like that. A vector is a little bit more complicated. A vector is a quantity that measures magnitude. So let's write down magnitude again. Magnitude and direction. Magnitude and direction. Now I've got a little clip here for you. You might remember this guy.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
So that was vector. And vectors have magnitude and direction. So if we take a look at this example right here, it says 70 miles per hour. Well, that's just the magnitude of it. We need to say which direction it's going. So let's say that it's going south. So it would be going down on this compass dial. And 50 pounds of force at 90 degrees. Okay, so things like that, they've got to have a magnitude and direction. That's what makes them a vector. Now we can represent a vector geometrically, so we can draw pictures of this using what we'll call a directed line segment. And in order to do this, we need some new vocabulary. So it says draw the vector from A, which is 0, 0, to B, which is 3, 4. So I'm going to go ahead and put those points on here. So we're going to put A right there, and then 3, 4. So this is over 3 and up 4. This is B. And again, a directed line segment would look like this. We're going to draw a line from here straight to there, and then we put an arrow on it so everybody knows that it's going that direction. If we put an arrow on it going this direction, it would be a different vector. So let's talk about the vocab. The initial point, that's where it starts. The initial point would be A. So in this case, the initial point is 0, 0. The terminal point is where it stops. It ends up stopping at 3, 4, so that would be at B, 3, 4. And then the magnitude, if we want to find the magnitude of this, we can do this using the distance formula or the Pythagorean theorem. Now, because we've got a picture of this over here, because we've got a graph, I'm going to go ahead and find this using the Pythagorean theorem, because I'm just going to go over here and I'm going to go over here, and of course we've got a right angle right there. So this right here is 3, and this right here is 4. So the distance from A to B, or the magnitude of AB, is going to be, let's see, leg squared plus leg squared equals the hypotenuse squared. So I'm going to do c squared there. That's going to be equal to 25. We're going to take the square root of both sides. So we end up with 5. Now I'm going to circle that. And again, notation here and vocabulary, instead of saying find the magnitude of something, we use what look like absolute value bars. So if it has absolute value bars over it, or around it, or double absolute value bars, double bars, and notice that this has a little arrow on the top there, that means it's a vector. Now this happens to be a harpoon arrow. You can use regular arrows also. So I just found the magnitude of that vector. I found how long it is. And then a couple other vocab words that are a little bit less formal. So the tail, that's the initial point. It's another name for the initial point. So that would be 0, 0. And then the tip would be 3, 4. Okay, so we've got initial point, that's where it starts. Terminal point, that's where it stops. Magnitude, that's how big it is. So we want to find how far it is from the tail, which is another name for the initial point, to the tip. So tail and tip, so let's make sure that we use those. Now, because the vector above has its tail at the origin, because its initial point is at the origin, what we call that is we call that a standard. It's said to be in standard position. Okay, sometimes we'll call that a position vector. Okay, but that's in standard position. And let's also talk about what equal vectors are. Vectors are equal if and only if they have the same magnitude, and I'm going to start abbreviating here, same magnitude and the same direction. They've got to have both. Now this if and only if means if we say they're equal, we know for sure that they have the same magnitude and the same direction, but it also goes backwards. If we know a vector, two vectors have the same magnitude and the same direction, then we call them equal. And it doesn't matter where they are, it only matters how long they are and in which direction they point. So we're going to look at example number 2 here. It says draw vectors AB, CD, EF, GH, and IJ if we've got all these coordinates right here. So let's go ahead and draw AB. So this is a new AB, so we're going to go from 1, 0. So 1, 0 is right there, so I'm going to label that as A. B is 3, 3, so we're right here, that's B. And again, we draw an arrow. Again, it's a directed line segment. That's what a vector is, represented as a graph or geometrically. Let's see, 3, negative 1, so we're going to go over 3 and down 1, so that's C. And D is 5, 2, over 5 up 2, so there's D. Again, we draw that line segment from the tail to the tip, so we're going to draw from C to D, and we put an arrow in that direction. Forget that I've got a little crook there. And then E to F, so 4, 7, so 4, 7 is right here, so that's where E is. And F is 2, 4, so over 2 and up 4, so that looks like this. We'll label that as F, going back this direction. And then negative 3, 0, negative 3, 0 for G, and then 1, 6 for H, 1 and 6, so we're right there. So again, this was G and this was H, and we go from the tail to the tip, so we go that direction. And then the last one, negative 3, comma 3, so back 3 and up 3. That one's I, and J is at negative 4, 8, so back 4 and up 8, so that's going to be right here. So we're going to head off in that direction, being about that long there. Now, it does say over here, find the magnitude. Again, that's the magnitude of AB. So I've got, let's see, I'm going to do this one using the distance formula. So I'm going to do a big square root, and I'm going to come over here and I'm going to do x2 minus x1. So that's going to be 3 minus 1. We used the Pythagorean Theorem before up there, so let's do it the other way on this one. So this is going to be plus, let me make that look a little bit better. So this should be a 3 minus 1 quantity squared, and then y2 minus y1, that's 3 minus 0 quantity squared. So we've got, let's see, this is 2 squared plus 3 squared. So that's 4 plus 9, and we get the square root of 13, which would be roughly, let me just pull the calculator up really quickly, second square root, 13, hop on the outside, about 3.6, 3.61. So 3.61, Okay, so that's how long AB is. So use the distance formula on that one, just using the initial and terminal points, the tail and the tip. Should be able to do it either way. We can kind of confirm this looking over here. We would go over 2, so one of the legs would be 2 and the other leg would be 3. Matches up with what we got there, so that should make us feel a little bit better. Now, do we notice anything about the vectors, any similarities or any differences? So I've got some marked out here. It says AB and CD, so vector AB and vector CD. So let's take a look at that. AB and CD, those are equal. They're equal because they have exactly the same magnitude. Again, we could check it using the same calculation, and they're pointed in the same direction. We could actually check the direction using the slope. If we take a look at BE and EF, or sorry, AB and EF, so AB is heading off in this direction, EF is heading off in this direction. If you'll notice, this has exactly the same magnitude, but it's heading in the same direction. So they have the same magnitude, but they have different directions. So that means they wouldn't be equal. And then AB and GH. AB and GH. Well, if you look at that, if you check the slope of the two of those, they are headed off in the same direction. They're angled the same way. They're pointed the same way. But GH is much longer. So they have the same direction, but they have different magnitudes. Okay? And then if we look at the last one, IJ compared to these other ones, okay, it is nothing like all the others. Okay? It's completely different. It's kind of out there on its own. Now, please note that if we slide a vector around, so if I take this vector right here, AB, and I slid it right on top of CD, it doesn't change the vector. So where it is doesn't make any difference at all. So sliding a vector around doesn't change the magnitude, or the direction. So because of this, you can slide them around wherever you want them to be, and they would still be the same vector. But we want to make it convenient, so here's what we do. We're going to slide it around so that the tail, the initial point, is at the origin. And if we do that, it makes it really easy to compare because they all start in the same place. They all start at the origin. So all we need to know is where they end. So where they end, or where they, I'm going to put where they stop. Okay? Where they stop, that's where the tip is. So let's go ahead and take a look at the next page. So the fact that we can slide a vector around and not change its magnitude or its direction leads us to the idea of component form. So let's write component form. Component form of a vector. Now, component form of a vector is really useful because it allows us to write a vector using only two pieces of information. So one is the horizontal component. So let's write horizontal right here. And the other one is a vertical component. So we just need these two things, a horizontal and vertical component. And this is going to look hopefully kind of familiar here in just a second. So component form looks like this. We've got angle brackets around two numbers separated by a comma, and A is the horizontal component. So the first one's the horizontal component, and B, the second one, that's the vertical component. And that should look kind of familiar. It's kind of like knowing everything about a vector, just knowing the x and y coordinates of only the tip. All we need to know is about the tip because we know that the initial point, the tail, is at the origin. So example 3 says, draw vector AB, then write it in component form if A is 1, 5 and B is 7, 4. So let's see what we've got here. 1, 5, so that's going to be right there. So there's A, and then B is at 7, 4, so over 7 and up 4, so it would look about like that. So there's B, and we need to go from A to B, so we'll draw that directed line segment there. So there's our vector. And then here's what we need to do. We need to take this and we need to come up with the components that form this vector. And the best way to do this is by taking the tip and then subtracting the tail. And we're going to write it a really simple way. We're just going to write take the tip and subtract the tail. That'll put it in component form. So let's see what happens here when we do this. So I'm going to start my angle brackets here, put a comma right there, and we're going to take the tip, we're going to take the x coordinate for the tip, and we're going to subtract the tail. So we're going to do 7 minus 1, that's a 6. And then we're going to do 4 minus 5. So 4 minus 5, that would be a negative 1. Now let's see how that works. Basically what we're going to do is geometrically, graphically, we're going to take this and we're going to slide it back 1 and down 5 so that the tail is at the origin. So if we take this one and slide it back 1 and down 5, we've got to take this one and slide it back 1 and down 5, and watch what happens. Back 1, down 5, that is where A is now, and back 1, down 5 would put it right here. So this is a copy of AB. And notice where the end point is right here. So if we count 1, 2, 3, 4, 5, 6, and then down 1, that is our answer. Now, it says, why do you think we use angle brackets to denote vectors? Well, the thing is, and this is what I was talking about when it says it looks familiar, this looks a heck of a lot like an ordered pair. In fact, we mentioned that you can tell what the vector looks like. You can tell all the information just by knowing where the tip is because you know the tail's at the origin. So it should look pretty familiar. So we can tell the difference between a vector and an ordered pair. Ordered pair, because there's a huge difference between this, 6, -1, and then having that in angle brackets. This just means the point 6, -1. This means the vector that goes from the origin over to 6, -1. Okay, now we can summarize this a little bit more formally. If we've got a tip and a tail, where the tail is x1, y1, and the tip is x2, y2, we can basically just use that formula that we're fairly familiar with. It's x2 minus x1 and y2 minus y1. This is the same as this. Those are just the same thing. I kind of like the informal tip minus tail method. If you want to use the other one, that's just fine, but it does relate pretty well with some stuff that we've done before. So on example 4, part A, it says, write the vector EF in component form without graphing if E is this point and F is that point right there. So this is going to be the tail and that's going to be the tip. So let's go ahead and do the tip minus the tail method. So we're going to do 2 minus the minus 2, so that's going to be a plus 2. And we're going to do 4 minus a minus 1, so that's going to be a plus 1. So in component form, this is going to be 4, 5. So we're going to go ahead and put brackets around that. There's our answer to that one. And then it says find the magnitude of vector EF. So we've got the vector EF in component form here. And it's important to point out that we could use the distance formula between E and F, and we could find it that way. But since it's in component form, there's actually a really simple formula to find the magnitude of a vector in component form. So if vector V is V1, V2, and in those angle brackets right there, so V1 is the horizontal component and V2 is the vertical component, then the magnitude of that vector is simply a big square root, and then it's going to be V1 quantity squared plus V2 quantity squared. So again, it's kind of like the combination of the distance formula and the Pythagorean theorem and all that sort of stuff. So on this problem right here, the magnitude of this one is going to be, we're going to have a 4 squared plus a 5 squared. So we're going to end up with a 16 here, a 25 here. So we get the square root of 41, so square root of 41. 41 is prime, so that doesn't simplify at all. But we can go ahead and pull up the calculator, and let's get a decimal for this. So let's see what we get here. We'll do second square root. 41, clear out of there, make sure that it looks right, and we get 6.40. So I'm going to do 6.40, and then everybody will know that we rounded it the right way. And then if we take a look here at these thought questions, it says, why did they choose to use 2 vertical bars to represent the magnitude? So the magnitude of a vector is represented by these vertical bars right here, or sometimes they're double vertical bars. Well, does that remind you of anything? Well, it should remind you of something. It should remind you of absolute value. Okay? Because when we deal with absolute value, we don't care which direction we are from 0, whether it's to the right side or the left side, positive side or negative side. We just care how far. Just like when we're talking about the magnitude of a vector, we don't care which direction it's pointed. We just care how long that vector is, how long that directed line segment is. And then it says, what would be the magnitude of the 0 vector? So 0, 0. So that means in component form, it starts at 0, 0, and it ends at 0, 0. So of course, the magnitude of that would be 0, and we could double check that by plugging it into the formula. Now we're going to take a look at a couple of real world problems right here. So it's important to kind of remember when we deal with real world problems, we're going to be thinking about the components, and it also says, hint, what does speed measure? So remember, speed just measures how fast something is going. It doesn't measure which direction it's going. So let's keep that in mind as we go through this. So on example 4, it says a plane is traveling east at 500 miles per hour with a tailwind of 150 miles per hour. Model the situation with vectors and find the resulting speed of the plane. So the plane is going 500 miles per hour east. So east goes off to the right here. So we're going to draw a vector that looks about like that. And we're going to say this is 500 miles per hour east. Okay, so here's the plane vector. And then we've got a tailwind. Well, the tailwind is pushing that. It's going in exactly the same direction. So I'm going to put a little vector right here to represent the wind. So if this is 500 miles per hour east, and this is also 150 miles per hour east, then the total speed of the plane, how fast the plane would be going, would be 650 miles per hour. Now that is just a scalar. If all we were asked to find is just the speed of the plane, it would just be this right here. So that is the answer. If we wanted to say a vector for the plane with the wind, then we'd say it's 650 miles per hour to the east. Okay, next one. A plane is traveling east at 500 miles per hour. So we're going to do the same thing on this one, make it about the same distance. Okay, so we're going to call that the plane. And then we've got it's 500 miles per hour. And then we've got the wind, but this time it's a headwind. So the headwind means it's heading in the opposite direction. And to make this a little more clear, I'm going to go in the other direction here. So it's pushing against it. Okay, so what that's going to do is it's going to have the effect of making that shorter. Now, I don't have to put a sign on here or anything like that, because the fact that we're saying it's a headwind, that would mean that it would be heading to the west. So the result of this is the plane is going to end up going slower, so it's going to end up going 350 miles per hour. Now, that is the speed of the plane. If we wanted a vector to represent the plane, it would be 350 miles per hour to the east, because it's still being able to head east. Okay, now let's take a look at the last one. This is kind of an interesting one that's going to lead us to some stuff that we come up with in the next few sections. It says a plane is traveling east at 500 miles per hour and a 150 mile per hour wind out of the north pushes it to the south. Okay, so let's model this the same way. So we've got the plane that's heading over here. So here's the plane vector. It's going 500 miles per hour. And then the wind is pushing out of the north to the south. So the wind is pushing against the plane going like this. Okay, so that's a 150 mile per hour wind right there. So I'm going to put a W on this to represent that vector. I should put a W right there to represent that vector. Okay, so here's what ends up happening. The plane actually gets pushed by the engines, it gets pushed this way. By the wind, it gets pushed this way. So it actually ends up traveling over here. Still going 500 miles per hour, but it gets pushed off course. So what we want to do is we want to find how long is that vector. So what's the speed of that airplane? So it's going 500 miles per hour this way. So this distance is 500. This is 150. So let's find the magnitude of that vector. We're just going to take a big square root and we're going to do 500 squared plus 150 squared. So we've got the horizontal component and a vertical component right here. And I'll throw that in the calculator. So let's see what we end up with here. So I'll clear that off. We end up with, and I'm just going to do a big square root, and then I'm going to do 500, I'll square that, plus 150, I'll square that. I've got everything, that all looks good, and I'm going to hit enter. I get 522.01, so that would round up. So 522.02, so 522.02, and that's going to be miles per hour. So that might be a little bit of a surprising result, and you might have a couple of other questions about this. I think we're going to narrow in on these ideas in the next couple of sections. You might look at that and you might think, well, hey, that's heading down. Doesn't that have to be negative? You might consider why that doesn't matter in this particular case. But this is just kind of an example. We've got each one of those solved. Let's go ahead and fill out the self-assessment and then take a look at problem number 1 on the assignment. Okay, I've got the assignment up here, and it says write the component form of each vector. Now, there are a couple different ways that we can do this. I'm going to go ahead and do the tip minus tail method to start off with. So here is the tail right here. It's at 1, -3, and the tip is at 3, 3. So if I do tip minus tail, I'm going to end up with 3 minus 1, so that's going to be a 2. Let's see, this would be 3 minus 3, so this would be 6. Okay, so that's the answer, but I want to show you a couple other things that we could do. We could do this graphically. We could just say, look, I need to know what the horizontal component is. So coming over this way, I go over 2 units, and then I go up 6 units. So you can literally just count. So over 2 and up 6. From the tail to the tip, we go horizontally to the right, so that's +2, and then we go up 6. So that would be the answer there. The other thing that we could do is we could take each one of these and we could slide them so that this tail is going to be at the origin. So I'm going to go back 1 and up 3. So back 1 and up 3 would put me right here. Back 1 and up 3 would put me 1, 2, 3 would put me right there. So I'm going to draw a picture of that. Notice that it looks the same as the original, and notice the tail is at the origin and the tip would be right here. That would be the point, and I'm just writing this down as an ordered pair. That would be from the origin to the point 26. So again, these right here, that's the end point, but if we put brackets around it, that's our vector. All right, good luck on the assignment.